Suppose a force of 20 pounds is applied to the end of a 10-inch long wrench at an angle of 30 degrees. Find the torque vector and its magnitude. If you were just asked to find the magnitude of the torque, this would be an easy problem. You could go back up and use, this is worth circling, by the way, this formula. If you're just looking for magnitude, and you know that angle theta between that the force is applying to the wrench handle, and you know the magnitude of the force and the length of the wrench, and you're just looking for the magnitude of the torque, this is a handy formula to use. It's real clear. But if you're looking for the torque vector, you have to think in terms of the cross product and drop the magnitude bars. So using this definition. And that's what we're asked to do here. So it's not as simple as it would be if you were just asked to find the torque. But in the homework, the magnitude of the torque. In the homework, I might have a problem where I just ask you to find the magnitude, and you could use this formula. Or even if I ask you to find the torque vector, you could maybe use that formula to check your work after you find the magnitude of the torque vector. So I think a good plan here is to draw this and to coordinatize things in a smart way to make your work less intense, less calculation intense. And there is a right way to draw this as far as ease of use. So let me show you that. So I'm going to coordinatize this so that everything's in the XY plane. However, remember the torque vector is defined by a cross product, so you have to look at 3 component vectors. So even though I'm only drawing what's going on in the plane, I have to add a third component of 0 to make the cross product make sense, because the cross product's only defined for space vectors. So, okay, so here we go. Here's the x-axis, the y-axis. You can coordinatize it any way you want. So I'm going to put the wrench handle on the x-axis, which makes a couple of the components actually 0. So it makes life easy. So the wrench handle, I'm going to say that this vector in red represents the wrench handle. And so what would so at this point, the tail is at 0, 0, 0, I suppose. So I know a representation for this torque vector. What would it be? If it's pointing in the positive x direction, the first component gets all the magnitude, right? So what's the length of this thing? 10 inches, right? So 10. And then the y component's 0. And then, of course, since we're doing it in the xy plane, the z component's 0. So I'm making that vector user-friendly by making 2 of the components 0. And then, okay, the assumption here is we're applying the force in the xy plane, right? If that's not the case, then the easy use goes out the window here. It's not as easy of a problem. So I can apply the force. Let me change the color here. So let me apply the force. Yeah, does that look like 30 degrees maybe? It doesn't really matter as long as it's fairly close. 30 degrees right there. That is F. Okay? Now, it's going to be convenient to put a copy of that vector so that its tail is at the origin, so that you can get the component form or think of it in component form and draw it in component form. So, and when you're drawing this by hand, you can just eyeball it. You don't have to use a ruler. Just the vector you draw here, make it look like it's parallel to the vector over here, because it's a copy of the force vector. They should be parallel if you draw a copy of it somewhere else. So this is a copy of the force vector. And what do I know this angle is between the positive x-axis and the force vector that I just drew? It's also 30 degrees because those 2 vectors in green are parallel lines, right? Parallel vectors. Cut by that red transversal, alternate interior angles again are congruent. You thought you were done with geometry, right? Whoops, that looks like 36. 30. Oh, okay, so we've got to come up now with the components of this vector. In other words, this point right here. The coordinates of that point would be the components of our vector now. So what's the trick for doing that? We know the length of this thing. What's the length of this thing? It's 20 pounds, yeah. Okay, so how do you get the first component? So I'll go ahead and write down the formula. It'd be 20, the magnitude of the vector, times the cosine of the angle. Does that ring a bell? That's the horizontal component. What would be the second component, the j component? 20 sine of 30. And then we've got to make it 3 components, so 0. And then what would be a better way to write this one? Well, I mean, the reason math books and math teachers make the angles nice is so you don't forget those trig functions of those special angles. It's not that necessarily you're going to get these nice of angles in practice. Although 30 degrees does come up a lot, 45 degrees comes up a lot in construction or what have you. So what's the cosine of 30? Times 20? 10 root 3. 20 times sine of 30? 10. Sine of 30 is a half, and then 0. So there's the vector you're going to want to use. So then how is tau defined? Tau being torque, the tau vector. So I didn't label it, but this vector in red is d, right? So we're going to take d cross f. Okay, let's create that 3 by 3 determinant. What goes across the top? ijk. And then what goes in the middle? If it's d cross f. Oh, and by the way, it is by convention d cross f, not f cross d. Why does that make a difference?
It's not commutative.
Yeah, it's not commutative. So f cross d would have the same length, but it would point in the opposite direction. So we have to have a convention here to get the vector that points in the same direction every time. So it is d cross f, not f cross d. If you're looking for just the magnitude, it doesn't make a difference. The magnitude will be the same either way. Okay, so what goes in the middle? The components of, 10, 0, 0, yeah. Components of d, right? And then the components of f? 10, 0. Everybody with me? So notice this is not because of all the zeros, this is not a tough one to find. So cross out the first column, you can see ignore the j and k, what's left? 0, so cross out first column, 0, 0, 10, 0. Is that going to give us much other than 0? No. Okay, minus, cross out the middle column, what do you see? 10, right? Cross out the middle column. What 2 by 2 determinant is left? 10, 0, 10 root 3, 0. When a column is 0, that's just as good as having a row of zeros. You're going to get 0. And then plus, I think this is the only thing that's going to give us something non-zero. Okay, what's left? When you cross out the last column, 10, 0, 10 root 3, 10. That's times k. Is everybody with me? So the first two zero out, what's left? 100 minus 0, right? So 100k, or if you prefer component form, 0, 0, 100. Now, why did I know that the first two components were going to be 0 ahead of time? Well, I mean, just geometrically, how did I know? Well, I'm trying to get to the right-hand system idea. So the right-hand system idea, okay, look, F lies in the xy plane, which is the plane of the screen, right? D, same thing, lies in the plane of the screen. We know that D and F and D cross F form a right-hand system. So D is the right hand or right arm. F is the left hand. You have to look at it when both the tails are at the origin. And that automatically determines where D cross F is going to point. So there's two choices, right? To have a vector that's perpendicular to the screen, you could go into the screen, in other words, going out the other side of the wall, or coming out at you, right? So you guys have to duck, like those of you sitting there, right? You have to make sure that vector doesn't hit you. Well, okay, it's got to be the one coming out at you, right, for the right-hand rule to be correct. So we knew the first two components had to be 0 anyway. And we could have, if we were just looking for torque, the magnitude of the torque, couldn't we have used this formula? So we could have taken, if you want the magnitude of the torque, of course we know it's just going to be 100 because when two of the components are 0, then the magnitude is just going to be the absolute value of the third component. So we could take the magnitude of this thing and get 100 that way, but we could have also used, if we were just looking for magnitude D times magnitude F times the sine of theta. And we know that the magnitude of D was, what, 20? Or was that the force? No, it was 10, and the force was 20. 10 inches, 20 pounds, right? And then sine of a half, or sorry, sine of 30 degrees, thinking ahead, which is a half, and there's your 100. And so if you could get that either way, right? But if you're only asked to find the magnitude of the torque, certainly this is easier than setting up this picture, right? What units? Inch, pounds.